Okay, yesterday we learned the regular falsy method. Aduna regular falsy method regular falsy method at its stage we find an interval which contains a root of the equation and then apply the iteration formula. And what was the iteration formula? This is the iteration formula. I repeat, in regular falsy method, at its stage, we find an interval x0 to x1, which contains a root, and then we apply the iteration formula. However, regular falsy method, there is a modified method, and this modified method is known as the secant method. Secant natraga second. Okay, so let me write it down. This modified method is known as the secant Secant SECANT. Secant method. Secant method or second method. Second method we choose x0 and x1 as any two approximations of the root. Kanagi root now, the root of f of x equal to 0. The interval x0 to x1 need not contain the root. Then we apply the iteration formula. Iteration formula, which is similar to the formula for the regular falsy method. And what is the iteration formula? The iteration formula is x1 equal to regular falsy x0 f of x1 minus x1 f of x0 divided by f of x1 minus f of x0. This was the iteration formula which we used for the regular falsy method. And for x1, the formula is the same. Regular falsy method second method in the regular falsy method, this interval x0 to x1, this interval should contain a root of this equation. Whereas in the second method, this interval need not contain the root. Root to yaurosuyai, yaudosuyai. Second method. Root to sigi marakta later. And then we apply the iteration formula. So x1 is given by this. In regular falsy method, what did we do? Then we calculated the value of the function at this point, and then we check whether the sign of the function was positive or negative. Check so that we choose another interval which contains the root. We straight away use this recursion formula. So x1 is given by this. Sorry, this is not x1, this is x2. X1 is so this is x2. X2 is given by this. After that, x3 is given by a similar formula. X3 is x1 f of x2 minus x2 f of x1 divided by f of x2 minus f of x1. Smailani, and this will continue and so on until x n plus 1 is equal to x n minus 1 f of xn minus xn f of x of n minus 1 divided by f of xn minus f of xn minus 1. Aduna, so the x2 we need not calculate, we need not check whether the value of this function at this point is negative or not, negative, whether positive, whether check the root to content over interval. We straight away apply this formula. So the formula is apply. The general formula is this: for n plus 1 approximation, it is given by xn minus 1 times f of xn minus xn times f of xn minus 1 divided by f of xn minus f of xn n minus 1. So the formula is apply to aduga magi geometric meaning geometric meaning in the second method we replace the graph of the function in the interval r. So let me share my screen. Yes. Can you see the screen? I think you can see the screen. Yes, sir. Here, here, this red line is a graph of the function f of x. F of x graph. This red line. So let me use color. What is the color? Let me use a green color. Okay. This red line. This is the graph of the function, and this is x0. This point is x0. This is x0. This is x1. X0, x1. Aduna, in the second method, we replace the graph of f of x in the interval x0 to x1 by a straight line joining the 2 points, by a straight line joining these 2 points. This point is x0, f0. This point is x1, f1. Aduna, sigi x0, f0 ki marak to label graph say this graph is replaced by this second. This second, this is a straight line which joins the 2 point x0, f0 and x1, f1. Aduna sigi in this interval x0 to x1, the graph is replaced by this second. Sigi second replaced tore, and we take the intersection of this second with the x-axis. This is the point where the second cuts the x-axis, and this is taken as the approximate value of the root. This is taken as the approximate value of the root. Aduna, I repeat, x0, f0 ziga, x1, f1 point, these 2 points are joined by a straight line. This line cuts the x-axis at the point x2. X2 is the cut. This x2 is an approximate value of the root. Where is the exact root? The exact root is here. The exact root is here, and this x2 is an approximate value of the root. Next, at x2, at this point x2, what do? We found out the value f of x2. X2 is the function की value से हमको खोले. So this point now is x2 f2. This point is x2 f2. This point is x1 f1. Now we join x2 f2. X2 f2 जिगा x1 f1 जिगा मुक join तोरे, and we extend the line so that it cuts the x-axis at another point x3. At this point x3. So this is the next approximation to the root. Next time, we calculate, we find the value of this function at x3. So this is the value of the function at x3, and this is the value of the function at x2. Next time, we will join these two. F2, x2 ka line. We will join these two lines. X2, f2 ziga, x3, f3 ziga, and is joined and it will cut at this point. Now this point is what? This point is x4. And so on. trying to some approximate root to some I repeat x0 f0 ziga x1 f1 go join tore it cuts the x-axis at x2. Now next time x2 f2 ziga x1 f1 ziga joined by a straight line, and this line is extended to meet the x-axis at x3. Now this is the next approximation to the root. Next time x3 f3 x3 f3 ziga x2 f2 ziga joined by a straight line, and it cuts the x-axis at x4. And then we continue this process until we get an approximate value which is within the limit that we want. Idea and a second, a second is this straight line joining 2 points on the curve. Any line joining 2 points on a curve, say this is called secant. Second second next approximation to the root theory never. Second next approximation to the root theory. This method is called the secant method. So let us discuss one example. Okay, let me stop sharing now. Come back to this. So let us discuss one example. Example of this historically. Okay. So ready. Let me write down the example. What is the example? Example E. Determine and approximate. Determine and approximate. Determine and approximate root of the equation. Root of the equation. Root of the equation x square minus twice x minus 1 equal to 0 using secant method. SECANT, secant method. And method starting with x0 equal to 2.6 and x1 equal to 2.5, rounded off to 5 decimal places. 5 decimal places. 5 decimal places. Compare the result. Compare the result with the exact. Compare the result with the exact root. Exact root 1 plus root 2. The exact root is 1 plus root 2. So let us find the solution. Let f of x equal to this x square plus twice x, x square minus twice x minus twice x. X square minus twice x minus 1. Starting with x0 equal to 2.6 and x1 equal to 2.5. The successive approximations are so x2 is given by formula x0 f of x1 minus x1 f of x0 divided by f of x1 minus f of x0. So what is this? This is, what is x0? X0 is 2.6. So this is 2.6 multiplied by f of 2.5. 2.5 minus 2.5 multiplied by f of 2.6 divided by f of 2.5 minus f of 2.6. And this answer, when you calculate this with the help of a calculator, this answer will turn out to be 2.419354484. 2.419354484. This is the answer you will get when you calculate it with a calculator. And f of x2, the value of the function at this point is given by 0.014562. This is x2. This is the value of the function at x2. Positive or negative or because now the new interval will be the interval containing x1 and x2. So x2 is solved double or new interval x1 to x2. That will be our new interval. Then using this, we'll find the value of x3. The next approximation is given by x3 equal to this one, x1 f of x2 minus x2 f of x1 divided by f of x2 minus f of x1. And this, we already know the values. What is x1? X1 is, we have seen that x1 is 2.5. And what is x2? X2 is 2.41935484. So this is given by let us put in the value. So x1 is 2.5, and the functional value is 0.014682 minus 2.41935484 into 0.25. 0.25. Then f of x2 minus f of x1. F of x2 is 0.014682, and f of x1, the value of the function at x equal to 2.5. When you put x equal to 2.5, you will get this value, 0. This is minus 0.25. And when you calculate this, you will find the answer that this is 2.41436464. 2.41436464. Secant answer star name. You will get this answer. Okay, so let me check the calculation again. This value is x3. Next we will calculate the value of the function at x3. Next up, we will calculate the value of the function at x3. Then using the next iteration formula, we will calculate the value of x4. And similarly, we will we will continue and we will find the values of x5, x6, and so on. So, proceeding similarly, proceeding similarly, we get x3 we get x4 equal to 2.4142138 x4 and x5 equal to 2.41421321356 sibo phangeba ko sai question da kari hagiba. Let us look at the question. Determine an approximate root of the equation using secant method, starting with these 2 points rounded off to 5 decimal places. Rounded off to 5 decimal places. How many have got? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Here we can see that up to the 5th decimal place of these two values are the same. Then it means we can stop here. Since x4 and x5 rounded off to 5 decimal places. Rounded off to 5 decimal places are the same. We stop the process here. We stop the process here. So the process to stop. Therefore, the required root rounded off to 5 decimal places is 2.41421. So this is the required answer, rounded off to 5 decimal places. Next, compare the result with the exact root. The exact root is 1 plus root 2. So let us compare this result with the exact root. The exact value of the root 1 plus root 2 is 2.41421, which is rounded off to 5 decimal places. Which is rounded off to 5 decimal places. Exact root approximate root up to 5 decimal places, the result is the same. Hence the computed root and exact root are the same when we round off to 5 decimal places, Aduna, this is an application of the second method. So the particular example is that the agreement was very good. The agreement turns out to be very good. So let us write this as page number 1. This is page number 2. This is the third place. This is third place, place number 3. Okay. So this is the second method. Second method for calculating the root of an equation. Next, let us consider another example. A top example, and see examples now. This example another method. Let us look at another method, and this method is known as the Newton-Raphson method. Okay, so let us look at another method, and this method is known as the Newton-Raphson Newton-Raphson Raphson method. This Newton-Raphson method is a very famous method. Wow. Okay. So this method, Newton-Raphson method, this is one of the most useful method for finding the roots of an equation. Suppose we want to find an approximate root of the equation fx equal to 0. Fx equal to 0 equation root find the so if this function f of x, this fx is continuous, then we can apply either bisection method or the regular falsy method to find the approximate root. Now, if f of x and its derivative f prime x are continuous, the function amasung magi derivatives is continuous oitaragadi, then we can use a new iteration method. New iteration method called the Newton-Raphson method. Called the Newton-Raphson Raphson method. Newton-Raphson method. And this method gives the result faster than bisection method or the regular falsy method. Bisection method is regular falsy method. The underlying idea of this method is due to the famous scientist or famous mathematician Sir Isaac Newton. Sir Isaac Newton na underlying principle of but the method that we now use is due to the mathematician Raphson. Raphson mathematicians method to never. Idea Newton the one due to Raphson. Okay. Newton-Raphson method suppose we want to find a root of the equation. Suppose we want to find a root of the equation f of x equal to 0, where f of x and its derivative f prime x are continuous. Let x0 be an initial approximation let x0 be an initial approximation of the root initial approximation and assume that x0 is close to the exact root. X0 is close to the exact root. Let us call it alpha. And the derivative of the function calculated at the point x0 is not 0. This is 0. So let me repeat. Suppose we want to find a root of the equation f of x equal to 0, where f of x and f prime x are continuous. This is the derivative of the function with respect to x. Let x naught x0 be an initial approximation, and let us assume that x0 is close to the exact root which is given by alpha, and that the derivative of the function at the point x0 is not equal to 0. So 0 is the Newton-Raphson method. Let alpha equal to x0 plus h. x0 is close to the exact root. x0 is exact root alpha ki manakta lai. Chapti manade. So x0 ga alpha ga ani si manakta lai difference. So the difference between alpha and x0, let it be h. So let alpha equal to x0 plus h, where h is a small quantity. Where h is a small quantity. Then we know that the value of the function at alpha, since alpha is a root of the equation, this should be equal to 0. And this is equal to f of x0 plus h. Alpha have the x0 plus h ni, this should be equal to 0. x0 chi alpha ki manakta lai habanina, alpha si x0 ti kamla pe. The distance of alpha from x0 is given by h. And since alpha is a root of this equation, f of alpha should be 0. And what is f of alpha? F of alpha is nothing but f of x plus h, where h is a small quantity. Then we expand this by using the Taylor series, Taylor theorem. Taylor series expand now expanding f of x0 plus h by Taylor's theorem, we get f of x0 plus h. This is f of x0 plus h times the derivative at x0 plus h square by 2 factorial times the second derivative at x0, and so on, plus higher order terms. And since this is equal to 0, we equate it to 0. F of x0 plus h have the f of alpha, and since f of alpha is 0, this whole series is equal to 0. Okay, then let us write on a new page. So you see, since series since h is small, we can neglect the terms containing h square and higher powers of h. Then we get what is the function? The function is f of x0 plus h equal to f of x0 plus h f prime x0. H is small, this h square term, this will be small, and all the higher power terms of h will be 0. So all the terms starting from this will be neglected. So what do we get? Only this thing, this two terms is equal to 0. These two terms is equal to 0. Then we get f of x0 plus h times the derivative at x0 is equal to 0. From this we can calculate h. H is given by minus f of x0 divided by f prime x0. H is given by this expression. This gives a new approximation. This gives a new approximation to alpha as x1 is equal to x0 plus h, and since h is approximately equal to this minus f of x0 by f prime x0, which is minus f of x0 by f prime x0. So you see, when we neglect the higher powers of h, we get this expression. Since the exact nothing, this is only an approximation. So when we add h to x naught, h exact value we should get alpha. Otherwise, the exact value we have neglected the higher powers of h. So this gives us the next approximation to alpha. So this x1 will be closer to the real root alpha as compared to x0. Already swine iteration now the iteration can be defined by x1 equal to x0 minus f of x0 divided by f prime x0. So x2 what this x0 will be replaced by x1. So this will be x1 minus f of x1 divided by f prime x1. x3 what x3 this now this x1 will be replaced by x2 minus f of x2 divided by f prime x2. And so on. Until xn is equal to xn plus 1 is equal to xn minus f of xn divided by f prime xn. So this is the iteration formula, and this is the equation 0. This is the Newton-Raphson formula. Newton-Raphson formula. Aduna x0 dagi next x0 dagi approximate closer to the exact root x0 dagi accurate root x0 minus f of x0 divided by f prime x0. x1 accurate root x1 minus f of x1 divided by f prime x1. So ultimately x of n plus 1 equal to x of n minus f of xn divided by f prime xn. So this is how we use the Newton-Raphson formula, iteration formula. So let us look at one example of this. Before looking at the example, first let us discuss its geometrical interpretation. Geometrical interpretation. Geometrical interpretation. Geometrical interpretation first let us draw a graph. Okay. This is x. This is the x-axis, and this is f of x. This is the graph of f of x. Okay. So has it. Suppose the graph of the function y equal to f of x. This is y equal to f of x. It crosses the x-axis at the point alpha. So this point is alpha. Record. Then x equal to alpha is a root of the equation f of x equal to 0. So f of x is graph na x is alpha. The kalkaradi alpha is the exact root of the equation f of x equal to 0. Let x0 be an initial approximation. Let x0 be an initial approximation. Let us call it x0. Let this point be an initial approximation to the root alpha. Real root na my approximation to x0. Then at x0, let us calculate the value of the function at x0. So this point is x0 comma f of x0. This point has coordinates x0 comma f of x0. At this point, we draw a tangent to the curve. At this point, we draw a tangent to the curve. This curve, tangent, and this tangent cuts the x-axis at this point. Tangent, it intersects the x-axis at this point. Point P korosi, T korosi. Tangent x-axis point. This is our x1 level. This is the next approximation to the root level. At x1, let us calculate the value of the function at x1. So this is the point. So this point is x1 f of x1. This point is x1 f of x1. At this point again, let us draw a tangent to this curve, and this tangent will cut the x-axis at another point. Now this point is x2. X2 function value. Then at this point, we draw another tangent to this curve, and then this tangent will cut the x-axis at another point x3, which is close to alpha. So in this way, we move closer and closer to the real root alpha. Tangent, this tangent comes from the derivative. So geometrical meaning of tangent the derivative to the curve. So this is what we mean by the geometrical interpretation of this Newton-Raphson formula. Okay, then let us look at one example. Example I'm going to see. This example is a geometrical formula. Okay, let us look at the example. Let us calculate the example on a new sheet. Example. Find a real root. Find a real root. Real root a root which is a real number find a real root of the equation x cubed minus 4x plus 1 equal to 0 using the Newton-Raphson method, starting with x0 equal to 0. X0 equal to 0 rounded off to 4 decimal places. 4 decimal places. I repeat, find a real root of the equation x cubed minus 4x plus 1 equal to 0 using the Newton-Raphson method, starting with the initial approximation x0 equal to 0, rounded off to 4 decimal places. Let us find the solution. let f of x equal to x cubed minus 4x plus 1. Then my derivative kaitarani, then f prime x will be this derivative of x cubed is 3x squared, derivative of minus 4x is minus 4. So this is the derivative. Since f of x is a polynomial and f prime x is also a polynomial, both of them are continuous functions. Clearly f of x and its derivative f prime x are continuous. Ti and QoQs are continuous everywhere. Polynomial functions are continuous everywhere. Aduna continuous what can we do? Any function function derivative since they are continuous, then we can use the Newton-Raphson formula. Newton-Raphson iteration method is and what is the initial approximation which is given? The initial approximation is x not equal to 0. Aduna the initial approximation is x0 equal to 0. The Newton's iteration formula, the Newton-Raphson iteration formula is x of xn plus 1. Xn plus 1 is equal to xn minus the function calculated at xn divided by the derivative of the function calculated at xn. Where n can go from say the 0 and nj, and can go from 0, 1, 2, 3 and so on. This is equation number 1. Putting n equal to 0 in equation 1, putting n equal to 0 in equation 1, we get the first approximation. We get the first approximation x1. X0 is an initial approximation higher, the first x1 is the first approximation correct. X1 equal to x0 minus f of x0 divided by f prime x0. And what is x0? X0 is 0. X0 is 0 ni. This is 0 minus. What is the value of the function when x equal to 0? When x equal to 0, this is equal to 1 and this is equal to minus 4. So this is 1 divided by minus 4. So this is nothing but 1 by 4. So this is 0.25. So x1 x1 is very simple. X1 is 0.25. Next, let us calculate x2. So let us calculate x2. To calculate x2, what should we do? We should put n equal to 2 in this iteration formula. So the iteration formula is data. We shall put n equal to 2. Okay. As data see, putting n equal to 2. Sorry, n equal to 2 nate. n equal to 1. Okay. I'm sorry. This should be n equal to 0. N equal to 0. This should be n equal to 0. X0 we don't ever say x0 origin. So n should be 0. So that we start with x0. So this should be n equal to 0, n equal to 1. We don't know that. This is second approximation. N equal to 2 n equal to 1. N equal to 1. Putting n equal to 1 in equation
First approximation.
1, we get the second approximation.
Initial.
We get the second approximation. The second approximation is x2 equal to x1 minus f of x1 divided by f prime x1. And what is x1? X1 is 0.25. 0.25 minus the value of this function when x equal to 0.25. We shall calculate it using a calculator. And then we shall also calculate this with a calculator. So first let me write it as f of f at 0.25 and f prime calculated at 0.25. This is equal to 0.25 is 0.25 minus this value and this value, they will turn out to be 0.015625 divided by minus 3.8125, and this is equal to 0.254098. This is equal to 0.254098. Basically, you should calculate this using a calculator. Next up, putting n equal to 2, we shall calculate x3. So similarly, we get x3 is equal to 0.254101. Already, question what did the question say? Find a real root of the equation x cubed minus 4x plus 1 equal to 0 using the Newton-Raphson method, starting with this value x not equal to 0, rounded off to 4 decimal places. 4 decimal places of the rounded of. So you should check whether the subsequent, whether the consecutive approximations to the root agree up to 4 decimal place. x2 ga x3 say, let us check whether they agree up to 4 decimal place. 4 decimal place. So what is the 4 decimal place? When I round this to the 4 decimal place, 9 labelina, this will be rounded up to 1 or never. 2541. Similarly, x3 2541. So the 0 labelina, this will still remain 1. X2 x3 since x2 and x3 rounded off to 4 decimal places are the same, we can stop the iteration here. So since x2 and x3 rounded off to 4 decimal places are the same, we stop the iteration. Here. Hence, the root is 0.2541. Stop. Okay. So this is one example of Newton-Raphson method. Newton-Raphson method ki example example we can consider one interesting example. And what is that? We can find this.
Rounding off is 3 decimal place. High road. X2 x3 ki magi rounded off 3 decimal place.
4 decimal place.
X2 ki value ka x3 ki value ka 0 point harga 254 amo oye 40 oye amana 2541 oye.
Oh, sige. 0 zigi matung the 9 leibani na ne. Sige value zi aina 4 decimal place for the rounded taro iragadi. I will write this as 0.2541 and enable 09 leibani na. Rounded off to 4 decimal place. Correct. Aduna sizu rounded off to 4 decimal place for iuda 2541 adun le enable 0 leibani. 4 decimal place for the rounded off taro panda manaba. Correct. Okay. Aduga ngasagi Newton-Raphson method se sigisi magi yam kana ba ko application harigadi ko to find the square roots of numbers. Correct. Aduna to find the square roots of numbers ida magi yam kana say for example let me write it here. Example. Say the find an approximate value of square root of 2 using the Newton-Raphson formula. Find an approximate value of square root 2 using the Newton-Raphson formula. So the solution, let x equal to square root 2. X is square root 2 square root 2 की value is x then square then you bring 2 to the left hand side, so this means x square minus 2 equal to 0. X square minus 2 equal to 0. Square the 2 z left side to pore. So let f of x be this function. Let f of x equal to x square minus 2. Then f prime x will be twice x. Now we have f of x equal to 0. F of x equal to 0. Now we have this equation, and then we have the derivative. And since f of x and f prime x, since both of them are polynomials, they are continuous everywhere. Function continuous polynomial they are continuous everywhere. Clearly fx and f prime x are continuous everywhere. Now this f of x, it satisfies the conditions for the Newton-Raphson method. Was it continuous or Aduna therefore f of x satisfies the conditions for Newton-Raphson method. For Newton-Raphson method. F of x f prime x then we can apply the Newton-Raphson iteration formula. Newton-Raphson iteration formula sorry, Newton-Raphson iteration formula we can find the root of this equation. The root of this equation will be nothing but the square root of 2. Iteration first we have to choose an initial approximation. First we have to choose an initial approximation. We can choose one. Choose x not equal to 1 is the initial approximation. Choose x not equal to 1 as the initial approximation to the root. The iteration formula is x of n plus 1 equal to xn minus f of xn divided by f prime xn. So, Srigidi putting ka Sig data equina line about we can substitute here for simplicity, we can substitute the values of these two values here, f of x and this. So let me show it here. This is nothing but xn minus, what is f of xn? F of xn is x square minus 2. X square minus 2. And what is f prime x? F prime x is twice x. Twice xn. This should be xn. There you go. And then you simplify this expression. Simplify this expression with the 2xn square is equal to 2xn square minus xn square will be simply xn square. There you go. Xn square. So this is nothing but 1 by 2 xn plus 2 by xn. This is question number 1. There you go. So xn plus 1 equal to 1 by 2 xn plus 2 by xn. See formula Z, we have come across this formula in one of our earlier Python programming classes. Python programming classes that formula we use this formula in a Python program to calculate the square root of a real number. This is a 2 formula from this we can calculate the values of x1, x2, x3 and so on. So let me write it overlay. So putting n equal to 0, 1, 2, 3 and so on, we get x1 equal to 1 by 2 x0 plus 2 by x0. And this is 1 by 2. What is x1? X1 is 1 plus 2. This is 3 by 2. So this is 3 by 2. This is 1.5. Next, x2 equal to 1 by 2 x1 plus 2 by x1. Now x1 is 1.5. So this is 1 by 2, 1.5 plus 2 divided by 1.5. And this value will turn out to be 1.416667 and so on. From x2 you will from this you will calculate x3 and so on, x3, x4, x5. There you go. So as a homework, you calculate x3, x4, x5, and then stop at x5. There you go. Aduga, the value of square root correct to 7 decimal places is the value given by x5. x5 x5 you will find that the value of the square root of 2 correct to 7 decimal places is given by this value, because x4 and x5 they agree up to the 7 decimal place. Interesting problem. So The method used in this example is applicable for finding the square root of any positive real number. So here we have calculated the square root of 2 using this formula, but you can use this method to calculate the square root of any positive real number. So if you want to calculate the square root of 3, then this 2 will be replaced by 3. Right? There you go. If you want to calculate the square root of 7, this 2 will simply be replaced by 7. I don't know, whatever the number whose square root we want to calculate, that number will be written in the numerator here. There you go. I don't know, Newton-Raphson method square root what was a. This is a very important application of the Newton-Raphson iteration method. Already, Magi advantage the Newton-Raphson method gives the root very fast. Masigi manam root say this method is very fast compared to the bisection method and the second method. So in general, if this magnitude of the derivative, in general, if the magnitude of this derivative, particular example is in general, in any application of the Newton-Raphson method, if the magnitude of this derivative is large compared to the magnitude of the function, then we can say that the desired root will be obtained very fast by this Newton-Raphson method. Newton-Raphson method ki magi limitation limitation suppose the derivative is f prime x ko. Newton-Raphson method ki general formula right Japan. Let's take it here. Suppose this derivative
0.
If this derivative is 0 in the neighborhood of the root, iteration we are moving closer and closer towards the exact root to neighbor. And in the neighborhood of this exact root, if this derivative is 0, in this case we cannot apply the Newton-Raphson formula because division by 0 is not defined. Division by 0 is defined. Exact root to manakta, if the derivative of the function turns out to be 0, then we cannot apply the Newton-Raphson formula. Another difficulty is that it may happen that this derivative is 0 only at the roots. Only at the roots. So another difficulty so that this can happen in two possible situations. That is, f of x if it has multiple roots. If it has multiple roots at the value alpha, derivative say at alpha 0 tarani. If this function has a stationary point, ID magi point of maximum OBI, point of minimum OBI at the root, then this derivative is also 0 at the exact root. F of 0 f of x magi exact root the stationary either maxima or minima f of x multiple root this process, this Newton-Raphson method, iteration method, can face some difficulty. Let me stop recording.